Hello there and welcome along to a little video that's going to go over the climate factors for your GCSE geography exam. Now let's remind ourselves first of all what we mean by the term climate. It is the average annual variation. It's a 30-year time period, and in particular it focuses on temperature and precipitation. It's what you would typically expect to have in a location. And there are 4 factors that affect the climate that we're going to have a look at: latitude, altitude, continentality, and prevailing winds. So let's jump in with factor number 1. It's latitude. Latitude is the distance from the equator. And if you take a look at this map, it shows you a very clear pattern. This is the January temperatures. As you move away from the equator, as distance from the equator increases, or as latitude increases, temperature decreases. You're absolutely right. So a little bit of a quick look at how we measure latitude. The units of it are in degrees, and it kind of helps, I think, if you think of a protractor sitting here. So the equator is known as 0 degrees, and that's because if you imagine a protractor sitting there in the globe, it's just coming right over to the 0 degrees. The North Pole, what do you think the degrees of the North Pole might be? Straight up to the top, and there it is at 90 degrees. So that's how we get the units for this. Where's the British Isles? Where's Northern Ireland? Well, we sit around about here at 55 degrees north, and if you've ever been up in Portrush, you might well have been along at a little restaurant called, funnily enough, 55 degrees north. So how does the latitude affect the temperature? So I want you to imagine here that we have got 2 equal amounts of radiation coming in from the sun. The radiation that's coming in at the equator is approaching pretty much head on, and this amount of radiation is just concentrated in this area. It's not really spread out at all. Whereas you come up here, the same amount of radiation here, look at how much it's spread out over that area. So if you take that amount and spread it out over a larger area, then any one particular place here isn't going to get as much heat as here. Therefore, it's colder than here. Let me give you an analogy that might help. So imagine that you've got your lovely hot toast just come out of the toaster, and you're going to put real butter on. I hope so. None of that margarine nonsense. Real butter here. You take the butter out, but it's quite hard to begin with, and you just set it on there. And let's just say in this case you decide just to leave it there. And in this case you decide to spread it out. You've got the same amount of butter concentrated here and spread out here. So which one of those pieces of toast would you prefer to bite into? Like, I like butter. Do I like butter so much that I want a huge big dollop of it right in the middle? Ooh, it's maybe a little bit much. Where it's concentrated, it's more intense. Where it's spread out, less so. And look, that's what we're seeing here. Where it's concentrated, it's more intense. Where it's spread out, there is less heat. So that's first element here, concentration. The next element is to do with the angle. And again, we're taking our same amount of radiation and we're bringing it to the Earth, and at the equator it's approaching more or less from above, more or less at 90 degrees, whereas up here at the poles it's approaching at a very, very gentle angle. That has some significant implications, and the analogy that's going to help us with that is this. So what makes for a good skimmer? Well, you need a good flat stone, of course, but the most important thing, as this guy is illustrating so well, is you get down low and you throw it at a very gentle angle. And if it approaches at a gentle angle, it's more likely to bounce off. Yeah, just like this. If it approaches at a gentle angle, it's more likely to bounce off, whereas it approaches at a steeper angle here, it's much less likely to bounce off. So that's concentration, angle. The last one is the thickness of the atmosphere. Now the sun's rays, the radiation from the sun, passes through the atmosphere before it reaches the Earth. But take a look at those 2 distances. Which of those 2 distances, AB or CD, is the greater distance? Yeah, you got it. CD is at a longer distance than AB. So the sun's rays pass through a longer distance of the atmosphere at the poles than they do at the equator. Now, what's the implication and consequence of that? Okay, so here we have incoming shortwave radiation from the sun coming into the atmosphere. And on the way down, first of all, some of the radiation is reflected back into space by gases in the atmosphere, which reduces the amount coming down through. And then some of it is reflected by clouds back into the atmosphere, which reduces the amount coming through. So as the radiation comes down through the atmosphere, some of it is reflected back out into space and the less of it reaches the surface. The atmosphere reflects incoming solar radiation. And if here the sun's rays are passing through a greater thickness of the atmosphere, then there's going to be more of them that are going to be reflected. Yeah, you're right. More of them are going to be reflected here. This is passing through a shorter thickness of the atmosphere and less is going to be reflected. So you've got the heat concentrated here, spread out here. You've got the heat, energy approaching at 90 degree or more or less angle here, gentle angle here, so more is reflected. And you've got the energy here passing through a greater thickness of the atmosphere, so more is reflected by the atmosphere. Therefore, it's warmer at the equator and colder at the poles. Okay, that's latitude, distance from the equator. Second, altitude. What do we mean by altitude? That's height above sea level. You'll have heard, if you've been on an airplane, we're approaching our cruising altitude now. It's all to do with height above sea level. So let's look at how altitude affects temperature first of all. I love this photograph, a fabulous little country in the world called the Faroe Islands, kind of between Scotland and Iceland. And there's something about the mountains and the hills in the Faroe Islands that just seem to have these contour lines that are kind of drawn into them. It's a really, really good way of seeing the height of the land. But as you can clearly see here, there is this point at which the air is definitely cold enough for there to be snow. Below that, there's not snow, which helps us to complete this. As altitude or height increases, temperature decreases. It's colder on top of a mountain and warmer down by the sea. Now, let's have a little bit of a think at this point about a Christmas song that you would be very familiar with. You sing this Christmas song a lot. I can't play the actual song here because I'll get a copyright strike on YouTube. But it's this song of Do They Know It's Christmas? And there is that line that they sing in the middle of it. There won't be snow in Africa this Christmas time. Now, I can't play the song, or at least the recording, so that only really leaves me with one option, doesn't it? Well, I'm going to have to play it live. There won't be snow in Africa this Christmas time. Only the bad news is that song's absolutely and utterly wrong. There will be snow in Africa in Christmas time. In fact, there'll be snow in Africa every day of the year. Unfortunately, that's a little bit of a stereotype of the continent of Africa. Why is there snow in Africa all the way through the year? Because we've just seen that the closer you get to the equator, the warmer it's going to be. Well, let's make our dilemma really difficult here. Let's go all the way down here to the equator, to Kenya, to Kilimanjaro, the tallest mountain in Africa. And look, what is there up on the top of the mountain? There is snow. There is snow in Africa at Christmas time every single day of the year. In fact, there is snow in Africa almost exactly on the equator because of this factor of altitude. So we're going to use the game of bulldogs as a little analogy this time to help us to understand it a little bit better. So let's let this GIF reset and then we'll talk our way through. So here is the heat. Just about to see it. Here we go. The heat that's going to be given off by the Earth. And the molecules of the air absorb some of that heat on the way past, warm up. But as you get higher into the atmosphere, there are fewer molecules of air. The air becomes less dense, so less heat is absorbed, and it becomes colder. Let's run that again. There's the heat given off by the ground. Lower down, more dense air absorbs more heat. But as you go higher up, the air is less dense, so there is less heat absorbed, therefore it's colder. So that's our little analogy. Let's take a look at a diagram to illustrate that. The shortwave radiation comes in from the sun and heats the earth, and the earth then heats the air above. The long-wave radiation is given off. Now, as we've just seen, the air is denser closer to the surface and less dense higher up into the sky. It gets less and less dense until you get out into space itself. And as the long wave radiation is given off by the Earth, because the more dense air lower down, more of that heat is absorbed, therefore the temperatures are warmer. You go further up, less dense air, less of the heat is absorbed, and therefore the temperatures are colder. So that's why it is that the temperatures get colder as latitude or as altitude increases. And you can see it quite clearly on this map here. This is a map of the average winter temperature over that 30-year period. And there's the hills of Scotland, the mountains of Scotland, and you can see that it's much colder here. The lowlands, and then the mountains here, and the temperature's colder here. Then you come down through the Pennines, the temperature's colder here. The mountains of Wales, the temperature's colder here. Dartmoor down here, temperature colder here. Northern Ireland, there's the Antrim Plateau, temperature colder. Sperrins, temperature colder. Mournes, temperature colder. The pattern is very, very clear. As altitude increases, temperature decreases. Now, how does altitude affect precipitation? Okay, so let's imagine that we've got some air coming over here, a body of water, and I'm going to use the analogy here of a sponge. Imagine that I'm dragging the sponge through the water and it's absolutely full up with water. In this case though, it's the air is picking up the water vapor, that's the gas as it comes over the sea. Then it meets the land, and as it comes to the mountain, it meets the hills and it rises, it's forced to rise. As it rises, it cools. Cold air can't hold as much water vapor, so the air becomes saturated. Condensation occurs, forming clouds and the possibility of rain. So in my analogy, I've taken the sponge here, it's full of water, and as I bring it to the mountain, I'm squeezing it. Can't hold as much water vapor. I'm squeezing it, and out comes all of the water on top of the mountains. Then we come down the other side. I've already squeezed the water out, and therefore it's drier on this side of the hills. So picking up moisture, water vapor over the sea, the air is forced to rise, it cools as it rises, cold air can't hold as much water vapor, it becomes saturated, condensation occurs, forming clouds and possibility of rain. Then because it's rained here, it's drier on the other side. So if you take a look at this little cross section here through Scotland, this time it's the average precipitation over the 30-year period. And you can see the pattern here if we describe it. Precipitation is rising here as we get to this side. That's because the air is picked up a lot of moisture over the sea. It's forced up over the mountains. As it rises, it cools. Cold air can't hold as much water vapor. It becomes saturated. Condensation occurs and the water is squeezed out. Now, in an exam, if you get a resource like this, you would have to quote figures. So look, that dark blue, what would you say the rainfall totals are using this key? Can you match it? Yeah, over 3,000 millimeters of rain. You squeezed it all out there, and by the time it comes over here, the rainfall totals are getting lower. So what's the lowest value you get here on the eastern coast of Scotland? It's that one there, which is that one there, and it's between 700 and 800 millimeters. You can see a similar effect here in Northern Ireland. Lurgan is actually one of the driest places in Northern Ireland, and that's because the moisture-rich air here travelling over the sea rises over the land here. It's squeezed out, and there's less of the moisture available down here, so Lurgan is actually quite dry. But we take a look here again at Scotland, though, that place that we looked at here. You can see initially it's rising, so we're getting these totals of rain, And then as it comes across here, the totals of rain are coming down again. We're not having quite as much rain at this point as we had before. There's that link between altitude and precipitation. Higher ground has more rain than lower ground. Okay, so it's latitude, that's distance from the equator. Altitude, that's height above sea level. The third one is something known as continentality, or distance from the sea. Now, for this one, here comes our little analogy. Imagine that you've decided to treat yourself. You're going to make yourself the most glorious cup of tea and a really, really nice piece of toast. In fact, that looks like a almost cinnamon toast with sprinkles over the top of it, maybe some nuts and things at the top of it, and honey and things like that. It looks absolutely gorgeous. You've made yourself this. You're sitting down in your kitchen just about to enjoy your lovely little toasty treat when there's a knock at the door. And you know what that means? It's the Amazon delivery guy. The package that you have ordered has just arrived. You flee to the front door, you open it up, you take the package from him, and you're so excited. Up to your bedroom you go, unboxing the package, and out comes the thing that you've bought, and you're so happy. You have to FaceTime your friends and send them photos and videos of it all, and then suddenly you remember, my tea and my toast. 10 minutes have passed in your excitement, and you come back down into the kitchen and you take a look at it. Question, is the tea still drinkably warm? Yes, of course it is. But your toast, it's cold. It's cold. It's cold. It was going to be so nice, but it's cold. So here's the point. Liquids cool down slowly. Solids cool down quickly. Liquids cool down slowly. Solids cool down quickly. Now hold that in mind, and we're going to bring this in to climate. So there's the land, is cooling down fast in the winter. The sea is taking a lot longer to cool down, right? And then when we go into the summer, the land heats up fast and the sea heats up slowly. The sea just takes its time doing what it's going to do. We're back into the winter. What's the land going to do? Oh, it's going to cool down fast. The land's very, very quick. The sea just cools down slowly. Then we're into the summer again. The land, oh, we're going to heat up really, really quickly before the land. We do everything really, really fast. The sea just takes its time, nice and slowly, and so on and so forth. Next winter, oh, the land cools down really, really fast. Very fast. And the land did everything fast. The sea, just chill. Just take your time. So the land heats up and cools down quickly. The sea heats up and cools down slowly. Okay, let's take that into this map of the world. This is January in the Northern Hemisphere, so it's winter. And we're going to take a look at this part here. Zoom in. Now, the sea is cooling down slowly, so the temperatures are quite mild there. Let's come all the way over here to the far eastern part of this huge big continental landmass, right? Really, really far from the sea. And the land is cooling down really, really quickly. Freezing. Like, not just freezing as in I'm cold, but like literally well below freezing. -40, -50 degrees perhaps. Really, really cold. And yet the sea is mild. Because it's just taking its time. That's the rush. We'll just cool down slowly. Okay. Question. What effect does that have on the British Isles? Now, we are land, so we're going to want to cool down quickly. But we're right beside this lovely, big, relatively warmer ocean. It's just cooling down slowly. It's very chill. Let's not get worked up about this. If we're right beside this, we're right beside a source of heat. Therefore, we are kept a little bit warmer. We're certainly much warmer than the temperatures way over here. Why? Because we're close to this source of heat. And if you look carefully at this map, the further east we go, what's happening to the temperatures? They're getting colder and colder and colder. The sea cools down slowly. The land cools down really quickly. The British Isles, because we're close to the sea, are kept relatively warm. Let's take a look at this little graphic here. So let's imagine this. The sea cools down slower in the winter, so the sea is warmer than inland areas. So let's say it's 8 degrees. The land cools down faster in the winter, so it's colder than the sea, let's say -5. What temperature is the coastal settlement going to be? Well, it's not going to be as cold as -5, is it? Well, it's not going to be as warm as 8 either, because it is the land. But it's going to be kept at a kind of slightly warmer. So what, maybe 3 degrees? Something like that, something in between. So areas by the sea are kept slightly warmer in the winter than inland areas because they're close to the sea. And then in the summer, of course, it's reversed. In the summer, the land heats up really, really quickly. Oh, we want to heat up as fast as we possibly can. Warm, 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 warm. We've got to be warm. The sea, we're going to take our time. There's no rush. We'll just chill. Let's cool. Let's warm up slowly. So the inland areas might get up to 25, 30 degrees. The sea maybe 18 degrees. Temperature here, 20, 21 degrees, something like that. You might have experienced that during the summer here if you go up to Portrush, Causeway Coast, on a really, really warm day. You leave Lurgan and it's like 25, 30 degrees. You get up to the north coast and it's 21, 22 degrees, something like that, because it's closer to the sea. So the sea in the winter cools down slowly, keeps the coastal areas warmer than inland areas. The sea during the summer heats up slowly, keeping the coastal areas slightly cooler than inland areas. And the distance from the sea affects the temperature you get in the summer and the winter. Okay, latitude, that's the distance from the equator. Altitude, height above sea level. Continentality, how distance from the sea affects temperature. And finally, a little something on prevailing winds. And to do our work on this, we're going to draw on some work that's going to come in the next subsection on air masses. These are large bodies of air that will blow towards the British Isles. Our prevailing winds here, the most commonly occurring wind direction, are typically from the west. And we have these two air masses that are the most common air masses that affect us from the west. You've got one that comes from the poles, it's polar. One that comes from the tropics, that's tropical. M stands for maritime because it passes over the sea. This is an old Latin word, maris, which means the sea. You might have been to maritime museums, all about the sea. So polar, maritime is coming over the sea. Tropical, maritime is coming over the sea. Because they're both coming over the sea, they're going to bring a lot of moisture and they're going to make the precipitation levels higher. So maritime air mass, if it's coming from the southwest or the northwest, you're going to have wetter conditions. Polar maritime, because it's coming from the colder air to the north, is going to have a cooling effect on the temperature. Tropical maritime is going to have this warming effect on the temperature. And those are the two most common air masses we get in the British Isles. Occasionally we'll have air masses coming from different directions, and so you can have one coming here from the east. This is known as polar continental because it comes kind of like from the northeast. Polar continental air mass, so in the winter when it's coming from here, it's going to bring very, very cold weather. And it also is a continental air mass. It's blowing over the continent, so it typically doesn't bring as much by way of precipitation or rain. Maybe sometimes a little bit of snow, but not very much typically. And we have a particular name for this one. This is the beast from the east. Can bring a little bit of snow, but typically it's a little bit drier than the other air mass because it's continental. And then very, very occasionally we can have this one. It's tropical, so it's going to be warm. It's continental, so it's going to be dry. Surprise, surprise, the warm, dry air mass is the one that is most infrequent for the British Isles. And these are the times that you can get the snow coming. Snow. Does that look like snow to you? Sand. Let's try that again. The sand is brought all the way up from the Sahara Desert that covers your cars, and it travels 5,000 miles to get here. So if it's coming from the sea, if it's maritime, it's going to bring more precipitation. If it's coming from the land, continental, it's going to bring less precipitation. If it's polar, it's coming from the north, it's going to be colder in terms of temperatures. Tropical coming from the south is going to be warmer in terms of temperatures. So those are the factors that affect climate. Latitude, which is distance from the equator. Altitude, which is height above sea level. Continentality, which is distance from the sea. And prevailing winds, which is our most commonly occurring wind direction.